Impressions on the design and analysis of diffractive beam splitters and light diffusers with VirtualLab Fusion. Today I want to show you two examples demonstrating some of VirtualLab Fusion's tools and capabilities to design, optimize, model, and simulate diffractive optical elements, DOEs, and their systems in which they are implemented, respectively. The two scenarios I'm showing are a diffractive beam splitter here on the left and a light diffuser here on the right. So for the splitter, we want to generate this light marking pattern. And for the diffuser scenario, we want to project our light trans logo high up on the facade of the building. But first, some words about our software for those of you who are not familiar with VirtualLab or light trans or Diffractive photonics. So what is VirtualLab Fusion? It is an optical modeling and design simulation software. Well, we are two companies. One company, Diffractive Photonics, is responsible for the development of our software, and Lighttrans International is responsible for actually everything which has to do with the customers. So we sell the software with a general distributor. We do trainings, generate use cases, examples, demos, give support and trainings. And I'm part of Lighttrans International. We are one big team. And together with a great team of international distributors, Fluentsoft, Wave Optical, TM Incorporated, Infotech, all over the world. So what is the specialty of VirtualLab? You can imagine that systems can be quite complex and consist of arbitrary sources, elements, types, and sensors. And VirtualLab provides you to control the accuracy, speed, balance, also shown here in this right depiction, so that you can define and decide yourself how accurate you want the simulation to be and as fast as possible, so accurate as needed and as fast as possible. And that's partly true for the methods used for different types of components and also for the free space propagations in between here. And this is done via a pool of interoperable modeling techniques on one single platform. So this is here used, this speed and accuracy balance on all these aspects of a system. So let's dive in our two scenarios. The first one is design and analysis of diffractive splitter generating a light mark. So here's an overview about the different steps of the procedure I follow here in our example. First, the general task. I'd like to know what I'm going to do, what are the specifications, what are the constraints, the requirements. Second, I build a basic system to know what is the spot size I'm dealing with in my system without my optical element to be designed. Then the next step is then I use our session editor, which is something like an existing wizard in VirtualLab. You'll see. This session editor helps me pre-configure the actual design and optimization document, the IFTA, or iterative Fourier transform algorithm, which is a very powerful tool which is implemented in VirtualLab Fusion. Then we do design selections, then system simulations, the structure design, because up to this part we still are in a functional regard and functional design steps or stage. But then we convert it to a structure and regard in certain structure effects. Then we do some final evaluations, and in the end, we do the structure export or show that it can be done, of course. So let's start here with the task. This is the actual task. I don't go into all the details. We have a Gaussian input beam. We'd like to have a diffractive beam splitting element of a binary type with a few silica structured on the second surface. Then an ideal lens for our simulation here, we assume we have a very good lens. And in a distance of 250 millimeters, we want to generate this light pattern but with separated spots. So each pixel or each pixel's center point indicates for the design algorithm the center of a deflected focus Gaussian spot. So the pattern should have a certain length of 15 millimeters. So now typically further requirements such as geometric requirements. Here let's assume we'd like to have a binary beam string element to reduce costs, for example. The smallest features should be about 2.5 micrometers. This ensures that we are in the range of about 5 times the wavelength, and therefore we can later on easily, with no critical thoughts, use conversion into a structure using the thin element approximation, which is typically valid for parallel scenarios, which is the case if we deal with feature sizes in that range. Here we specify a certain position accuracy, and you specify, or let's say we want to specify the pattern via this different. For merit functions requirements, we'd like to have a conversion efficiency for our pattern of 60%. The stray lag should be below 5% and the uniformity error below 2%. The basic system looks like that. We have the collimated input beam and focusing and getting a spot of that size here. Okay. Now, with the actual element we designed, this focus spot should thus be deflected to different positions, here indicated with these center circles. Now, VirtualLab allows you to use assisting tools, our so-called session editors. Normally, you would have, or you could use the IFTA document directly and also build up your system from scratch. But these session editors are a great help, especially for parallel systems, but sometimes even for non-parallel systems as a base at least. So for that, this is already some screenshots of our graphical user interface. At start, diffractive optics. This pops up this list of different optional session editors for here beam splitter designs and diffuser designs. Now we're using the arbitrary array beam splitter session editor. By clicking here, this window opens, which is our session editor, which guides you step by step through the configuration of the design document. So you see, after going through that whole document and clicking then to finish, it automatically generates an optical setup, the system in VirtualLab, and further document the so-called iterative Fourier transform algorithm optimization document. And they are already pre-configured, so it starts already on the design page and not on the specification page. Of course, the more you know, you might want to do some further changes, adaptations, tuning, then you might have a look also on the other pages here. But typically you just click start and get first results. Let's have a look at the IFTA. So here at the design page, you click first on start design, then depending on the numerical effort, how many sampling points your design needs, it takes a few seconds to some minutes, and then afterwards the resulting or designed transmission function can be shown by clicking to show. And here it looks like this in the face view. On the analysis page, the IFTA is a very powerful tool which also has analysis and tolerancing options. Here you see already the evaluation of three selected merit functions: the conversion efficiency, CE, the uniformity error, UE, and the maximum relative intensity of stray light, SL. And they look already quite nice and fulfill our requirements. And here you see also the results in the view of the IFTA. Actually, this is not the separated Gaussian spots, but you see these pixelated spots because each pixel represents the efficiency of one diffraction order. Later on, we'll see at these positions of each pixel the actual Gaussian. Here, the right figure shows the same results in a false color scheme that you can see more clearly the stray light orders, which also exist. Somewhere the algorithm has to put also the stray light too. Now let's have a look about how we decide which design is now the best or a suitable one. For that purpose, we should also consider some tolerancing simulations. This can also be done on the Analysis tab of the IFTA. So you see the lower part here, we choose a Scan Scale Error Range. So we tell VirtualLab it should emulate as if the element will be too shallow or too deep, so that the phase differences which are introduced by the element are either too low or a bit too high. Here we chose a range of -3 to +3%. And after the calculation and then show a diagram, we get here for the three selected merit functions the curves for 101 data points. What can already be seen is the conversion efficiency stays of the whole range quite stable. You see, we are always at about 63%. The same is true for the maximum relative intensity of stray light. There is a strong curve, but if you check the scale for the y-axis, you see this is all quite stable. Actually, it even gets slightly better if we deviate from the ideal height. Well, still, it is the ideal height, because if you have a look at the uniformity error, this changes more dramatically if we are if the fabrication, for example, shows a stronger etching depth error. You see then the uniformity error goes even up above 8%, quite symmetrically. Well, we have a binary element. So let's have a look how other designs behave. For that purpose, VirtualLab provides you the so-called multiple run document, which automatically does a certain number of designs, and you can filter these designs for certain desired values. Here I say I'd like to have an overview of which result of my 100 designs show a greater conversion efficiency than 60%, uniformity error with less than 2%, and maximum relative intensity of less than 5%. In the end, I decide, well, you're getting then a list where you can select which of the 100 or those elements maybe which fulfill all your desired requirements, which look the best compared or give the best compromise. So here I have at the end 4 different candidates, and you have all of them have behaved similarly regarding the stray light and the conversion efficiency. So I only have to look at the uniformity error. And you see the here in green I have marked the requirement line of 5%, and you see the candidate 3 and 4 show for my tolerance simulations that they show higher uniformity errors if the tolerancing is plus minus 1% and it is in the range of 1% negative or positive. Here, scarcely. Candidate number 2 stays below that line, but it's still very close. Only element or candidate number 1 clearly, and if you want to play it safe, then I would choose this element. The other requirements are fulfilled for all of these elements, even with the tolerance, within the tolerancing range of plus minus 1%. Well, you've seen I depicted it by 3 to see how it would behave even outside the required or specified tolerancing range. Now to the system simulation. For that purpose, the session editor has already pre-configured also the system, and we have the Gaussian wave. The aperture together with the beam splitting element represents the phase element, Then we have this ideal lens and a 250 millimeter distance, a camera detector. And simulating that, a few seconds later, we are getting our nice pattern. And if I zoom out this center area, we see that here also, and if you look closely, you see also some trailer, but they all are below the specified values. Now we come to the structure design. So based on the design transmission function we use in the design ribbon, the optical structure design, and then via the interim edit dialog, we generate the actual structure model, here consisting of two elements. So compared to before, we had the aperture and the beam splitter. The beam splitter is actually an infinite because it's periodic element, and the aperture specifies the size. So together it forms the phase element. And now we just adjust the linkages. So instead of up here, we just move the mouse down here to the plane surface and the diffractive optical element, and together they build now the real element with one surface, few silica and 1 millimeter distance, and then the structure on the second surface. Structure representation is proportional to the phase representation. That's a typical aspect if we are in a parallel domain. So here is also a 3D depiction of the structure. And now let's see for what purpose this conversion was also helpful regarding simulations. Let's assume we, let's see this result from the simulation based on the phase function. And if we do the same now with the simulation based on the structure profile, we see they look almost identical. But if you have a look at the maximum of the legend here, the scale, you see there is quite some difference. That's due to Fresnel effects. So now you can do also certain tests for coatings. Here I apply now an anti-reflection coating for our wavelengths in the range of 532 nanometers. It's fitting here. And if I simulate again, then we are again back in the range of the initial design, initial simulation result. So another example where the structure is of relevance is to deal with multiple wavelengths. Such a diffractive optical element is typically designed for one specific wavelength. And if we use now our triplet of RGB, you see for our green wavelength, it is perfect here. Here the zoom center area, but for the others, we have either getting a smaller pattern or a larger pattern, and the zeroth order here, well, here they are overlapping. Here separately shown in VirtualLab, you see they are not uniform with the other diffraction orders. So now for the final evaluations. We deal here with a pixelated structure. So if you have a look at the designed element, and if you fabricate that with a mask etching technology, lithography, then there will also be this rectangle or this square pixelated structure. And it's a physical effect that if such square structures which are equidistant are interacting with light, or the opposite, light is interacting with such structures, a certain sync modulation appears. You see here the sync function, and in their nulls, the so-called higher sync orders appear. So here you have the result with the straight-line orders shown. If I make the output field larger by a factor of 3, you see that in the outer areas we get our desired pattern again, but with a much lower efficiency. And if we make an output field even larger, then if we simulate this pixelation factor of pixelation correctly, we see that even here we see the higher sync orders. But luckily they are at the nulls, so they really carry quite low energies. But nevertheless, they carry energy, and that's also why they pose certain limitations for the achievable efficiency that can be reached for the actual main pattern. So of course, at some point, we want to export our data to pass on the information for the manufacturer. So this is quickly done. VirtualLab is built in a very modular way. So really go to the element, then to the surface, and the surface say, I'd like to export that. And then you can define what kind of export. And here we chose, of course, a mask export. So we're getting here the mask scheme as a bitmap. And additional information which are helpful for the manufacturer, such as the size, what is the total profile height, number of masks, and so on. This brings me now to the last summary of the first scenario, this beam splitting scenario. We had this task here, and everything which is here embedded in this red area is done in VirtualLab. So we started with an assisting tool or a session editor. This output two documents, the system document, the optical setup, and the IFTA, the design optimization tolerancing tool. And from this design tool, this is this arrow here, we are getting automatically, well, the result is automatically passed on to the system, which can be instantaneously practically simulated. And after structure design, you can even do the design, the simulation based on the design with structure effects and material effects, Fresnel effects, and such, and do the export, the fabrication export. And you can generate results via this optical setup or via the IFTA itself and get the evaluated merit function values of the design result. That was the first example, the beam splitter example. The second example is design and analysis of system with diffractive light diffuser, generating the light trans logo. Again, here an overview about the procedure or the steps I want to show. This time without structure design, structure simulations, structure export. This would be equivalent to the first example. First, I'd like to know the task, the requirements, and specifications. In the second step, I check the pattern, the beam conditions. Then I do a test design, you'll see. Then I prepare for the final design data. Then I do the design and check the merit functions and simulations. Then I optimize or check, improve the results. And at the end, I introduce an aperture task. So this is our task. Let's assume we have here a garage and want to put here a projector and project a huge light trans logo high up here on that building. So we have a Gaussian laser beam. There are also other options to generate light patterns with LEDs or with lasers. Particularly lasers have a higher power, higher efficiency. And with our diffuser approach, we are getting also even higher efficiencies than with other methods, pattern generating methods, such as stencil methods. We'll see later. The pattern should have a size of 4 meters in width on a projection area of 4.6 meters times 2.46 meters. And an additional requirement is that outside of that area, maybe a bit better because you have to adjust the whole thing, there should be no stray light. The UE should be an alone element, meaning there should be no further optics. So regarding the pattern and beam conditions. So this is our imported bitmap of our logo. And when we import that, first step what we do is we mirror it, because by default, VirtualLab regards the light always as if you're looking into it. And if the beam generates something, then you would see the field now as you could read it. But we want that it be that is reflected from the wall. We don't simulate the reflection here, so we just assume, okay, how does the light come out of the element, meaning we have to mirror it, and that's why I did that here. Then after the import, Virtual doesn't know what its size, so I adjust also the size to be 4 meters, and then I check what are the smallest details in my pattern. And here I see they have a thickness of about 14 millimeters. But that's not the final value, because we have this situation. You see, we have an inclined illumination of the wall for protection. But the IFTA, which we will be again using for the design here, is meant for the optimization between the plane here, the transmission plane, and a parallel plane in a target, the target position. Meaning here, this yellow plane here. So, but we want to have a nice pattern in its red plane. Therefore, we have to somehow calculate how would the pattern look like in the yellow plane, which is relevant for our design algorithm. And this is easily done with a different simple system VirtualLab. Actually, what we see here is the element works, or from the element itself, it is as if there is a spherical wave going up to the projection area, but only at the positions where we'd like to have the pattern light is should be hitting there. So we have a spherical wave in 15 meter, because that can be analytically simulated inside that element. And then in 15 meters distance in our desired plane, we specify an aperture stencil, a function of our desired pattern, because here we'd like to have the perfect pattern. And if this is like an aperture, meaning everything afterwards, everything outside of the pattern is cut out. So meaning we have just the spherical wave portions of the pattern of the light translogo pattern. And then this part we are propagating backwards in this yellow plane, indicated with these green arrows. You see this here. So we have this spherical wave in 50 meters. Then it hits this stored function where our pattern is located. And this is the rotated plane by about 50-60 degrees. And then we propagated it by backwards propagation into the yellow plane. So just simple done. And this produces just a geometric distortion, namely here, where we have done it for a test pattern. So from our light translogo, we do first a test. So I choose some details where we have smallest features of our pattern. These I push just together. You can do this via graphics tool or in VirtualLab itself. Then we put this pattern here into our stored function, and then we simulate that, and we're getting out this result. And you see this is now compressed in y direction because we have this tilt angle. And here we see now we have smaller details. Now instead of 40 millimeters, 10 millimeters. So this can quickly be done with a pre-distortion. So this is now our desired design target pattern for test pattern. So what should be now the target pattern sampling? At the end we chose 5 millimeters. And you see with 5 millimeters our pattern looks quite rough, but you'll see that this will be smoothed out because the spot sizes, the spot shapes are round and they are overlapping and they will form some smooth contour. At least that's what we expect, not what we hope for a classic diffuser. What you see here is also a curve generated by VirtualLab, where we investigated what are the 1 over e squared diameters of on-axis spots in 15 meters distance. And depending on the 1 over e squared waist diameter, so the input beam. And you see, of course, smaller beams, input beams, have a stronger divergence. So in 50-meter distance, they are quite large here, almost, 20 millimeter diameter. But with 20 millimeter diameter, we can hardly generate nicely a pattern which has the smallest lines here of 10 millimeters. So that's why, and because this is a demonstrational example, we choose here a value of 10 millimeters, which will still make our small cities a little bit wider, but in any case, we would expect a certain soft edge of our pattern. So that is totally fine. You see, we could choose also smaller spot sizes, but as I said, it's a demonstration example which I'll be also using for trainings and use case, and I want to show certain things with that. So, well, you see there are certain limitations. What sizes can be reached without further optics? So, but in any case, we could use smaller ones. But we use a value in between of these two red lines here, and they indicate what we will be checking. So we will make an ideal diffuser with this size, 10 millimeter spot diameter, and then we will illuminate later on this element, which is optimized for that size, at least for an ideal diffuser condition. But then we will have a larger overlap by using here larger spots and smaller spots to reduce the overlap. The ideal diffuser condition is shown here, that if one spot is here, its diameter should be double of the distance of these two neighbor spots. So we will play a little bit with these distances by generating different sizes. So why do we do a test design? It helps us, well, first of all, why do we do it with a test pattern? Because sometimes the full pattern takes much more time, is numerically takes more effort, and maybe even the simulation of the full system can't be done. Then in any case, we still want to have some impression of the light texture. And all that can be done with a test design. So like in the first example, we make use of a session editor. This time we use the pattern generating diffuser session editor. And here, after these 14 pages, we are getting again a pre-configured IFTA design and optimization document and the optical setup document for the system simulation. So, and now here 3 results. Result number 2 corresponds to an input beam where the ideal beam light diffuser condition is met. We have a nice speckled pattern. If we use a smaller beam, which generates in 50-meter distance a larger spot, then the speckled patterns, speckles get larger, and we are getting also larger areas where we don't see any light anymore. And also the maximum of within them, these light speckles, are higher. So it gets more extreme and rougher. If we have less overlap of the spots, you see more and more already the gridded structure of the pixelated bitmap which we had. This is already an interim result for it's not yet a beam splitter, but it does not fulfill the classic diffuser condition, so it's something in between. But sometimes this pattern type is also recognized, and it's a matter of taste. But for example, we choose the ideal diffuser condition, meaning a beam weight of 1.25 millimeters. Next, we do the preparation of the final design data. So what we have not talked about yet was what about the zeroth order? Typically, when you fabricate an element, there is an height deviation, an etching depth error, a tolerancing for that. And that's why, well, in the first example, it was not that important, because if the zeroth order it was a little bit higher, okay, maybe it was not that disturbing at first. And secondly, even in our tolerancing simulations, it was within the allowed range. But this time we don't want to have any higher area here. And we will also do here a 4-level design, or maybe an 8-level design, and then it becomes more and more complex to have a really optimal structure height. So typically there will be a 0th order error. What can be done? What can we do? We just shift the pattern so that the 0th order can be blocked out. But of course, this alters also the geometry, but that's no big deal. Instead of this condition of 50-meter distance to the center of our projection area, we say that the projection area center would be here, this edge, but actually the center of the pattern is a bit above that. But you see the angles change a little bit, and the values here. So we are using now this geometry for the final pattern. This could be also done for the test design, but it was not necessary. It is very similar here. So this slide shows you some areas of interest. When we have here our laser and the plane of the diffuser, then we typically want to cut out or to truncate the outgoing light, namely want to truncate and fade or block the stray light. As was mentioned before, there should be no light outside the projection area, because otherwise birds, animals, and helicopters and such could be disturbed, and also light which goes below the projection area could go into the right and left of the projection area, and also below into the windows. Both is unwanted. So that's why we are interested in a so-called optimization area for the design, the actual pattern area. And then somewhere in between, we'd like to have the area where we place an aperture for the blocking of all the light. So let's do the full design, check the merit functions and simulations. So again, with the IFTA, I did the designs. And here I show you the 6 IFTA results for different settings or different design types. First, here, the first column represents continuous designs. The upper row show you always designs where I optimize just the light trans pattern text. And below, I tell the optimization algorithm that I'd like to have a rectangular area around my logo, which is the so-called optimization region. And within that, the algorithm should try to reduce the stray light so that we have a good contrast. And you see this works well. So the stray light is higher, of course, but it is pushed out of that area. In the second column, we have, again, above the optimization for just the pattern, below with this extra optimization region with this rectangular or this trapezoidal one, but with an 8-level design. And the last one is the 4-level design. The less level, the less continuous, the less freedom you have, the worse the result. You see, we are getting much more stray light. You have to consider that this is a false color view. And I depicted that so that you can see clearer the effect. So next we'll have a look about how the result would look like in a system for the two extremes. The best pattern from the continuous result and the worst pattern from the result where we have also strongest stray light, worst uniformity error, because we have the strongest requirements, the strongest constraints for the algorithm. So here you see our system, also generated by our session editor, the Gaussian wave, the aperture, the diffuser here, and here we place a universal detector to evaluate the irradiance. So because that's what people are more interested in, well, for parallel systems, the irradiance is totally proportional to the sum squared amplitudes. But nevertheless, I wanted to show that this is easily done, that you can do radiometric evaluations. So the left results are from the continuous transmission with optimal region be the light logo, and the right result is from the 4-level transmission with the optimization region being the rectangle. And you see in the real colors where we emulate the eye perception, you practically don't see any difference. Well, here you see a little bit that the stray light was pushed out, but the pattern actually, you can really see a big difference. And that's because, you'll see we have quite a strong uniformity error. Well, of course, here we have a uniformity error of 0. Here it's around 20%. But in any case, we do have speckles which have a contrast of 100% from 0 to 100%. And if now two neighbor spots do not have both the same uniformity, it doesn't matter much. They overlap and will, in most cases, because of the phase differences, have some constructive, destructive interference and won't show perfect double values or so. So the mixture does the trick here, and in both cases we have good results, meaning we can use the 4-level transmission, which is much cheaper to fabricate. Actually, a continuous transmission, not all methods would work, and sometimes even special kinds of methods would be required. In the lower result, you see, because of the reversed rainbow color scheme, that we have nicely pushed out the stray light. And if you look closer here in the zoomed area, there is a little bit stray light to be seen around the actual pattern, but only in its false colors. Nevertheless, maybe there are certain weather conditions where this could be seen more clearly, and that's why we choose the 4-level, which is cheaper, with this additional optimization area. Now that we have decided about what kind of design, we can optimize that one. So for that purpose, we just use the tuning factor or tuning tool, the so-called goal efficiency parameter. And by that, if I increase that, it's a pushing parameter. You can specify even higher values than 100%, as you see here in the first column. Of course, they cannot be reached, but it just pushes and tells the algorithm to try harder to reach a certain goal efficiency at the cost of other merit functions. Namely, here the conversion, the uniformity error. Actually, here it's only the uniformity error, but that drastically increases the resistance intensity of stray light. Luckily, side effect positive one goes down. You can imagine if I force that more efficiency goes into the pattern, that where does the light come from? Well, it can't come from the higher sync orders because they are physically not to be removed, but from the stray light, so that's reduced. But of course, it's a strong constraint for the optimization design algorithm, and therefore it can achieve better uniformities. But as we have seen, the uniformity error is not of big relevance, so we make use of that. And you see, in the beginning, where I haven't used this tool by default, we got an efficiency of about 30%. Well, let's have a look here at the conversion efficiency, because here you also see what goes into the optimization region. So about 30% conversion efficiency into our pattern. And we achieved about 55% at the end for our optimized design. That's good. And here you see in 3 enlarged results displays our final simulation result. Here in false color, reverse rainbow logarithmic, so you see clearer also the effect of the used optimization region. And here in real color with the emulated eye perception, with a very nice uniform result. So what's next? Well, a comparison. I explained in the beginning about the efficiency. Well, let's assume we would use another pattern type generating approach where we have an illuminating beam which hits a stencil, an aperture with our pattern as a stencil, and then propagate it further to the design target area. We would get the light just which would go through this stencil area. And you can imagine we lose much light. Here only 4% goes through that center area. Well, that's just a rough calculation, I know. Nevertheless, it should give you an impression. The diffuser approach yielded about 55%, which is about, well, 10-15 times higher. And additionally, for our application, we benefit from these speckles, which give a flamy, more organic characteristic, or has a more organic nature, which is fine for a light trans logo where we deal with light. And yeah. So now let's introduce the aperture, which blocks out the stray light. So actually, well, let's go back first. There are different options. Well, we could propagate the field into different positions and see if you could apply there the aperture to block out the stray light. But it's possible that at some positions the calculation would take quite some time because of the numerical effort, because we are not in a far field. Approximate methods are not possible. It's not very close to the diffuser, so maybe rigorous methods are also taking more time and more RAM of your machine. So that's why I wanted to show you here a method how you can calculate the size of your pattern, and if you can apply it certain position, an aperture, which is much simpler and requires low numerical effort. This is the tool of the mathematical convolution. For that purpose, I calculate how does the simple spot look like in a certain position, here 300 millimeter distant from the diffuser, and then I do again this backwards propagation, but it's not just to the parallel plane, but even go backwards to the diffuser until we reach 30 centimeter distance from the diffuser, and calculate how would the pattern look like there. So now I just have to convolute these two fields, and then I see, okay, because that spot would be deflected into all these positions indicated by the white pixel. So here I need more pixel, but doesn't matter. This is the pattern effect. And we are getting then this convoluted result. And I've also used a nice tool in VirtualLab which make an automatic detection of where are 99.999% of the summed amplitudes. And you see inside that dashed selection area, we have nicely our pattern. So now let's see if this is also inside the optimization region, which corresponds to our projection area. So I do the same thing here. I illuminate the optimization region and propagate it backwards. And then I see, of course, this distorted optimization region. And this I just add up with my previously gotten convolution result. And then I see, okay, it is nicely inside my optimization region. I have enough space here for an aperture so that I really just let the light of my pattern go through and only reduce stray light within my optimization region, and everything outside is blocked so nobody can be disturbed. So now let's see. Well, actually that would be it. Well, not yet, because I also checked what does the zeroth order look like. The zeroth order would be inside my aperture. Of course, it's unwanted, so I just add an additional aperture. So that would be actually my whole design task. Now I could generate the structure, give this to the manufacturer, tell also the manufacturer to generate this aperture element, and now I put everything together, assemble everything, and I have an element. Well, if it's possible for numerical effort, it's also nice if I could simulate the whole system with even with the aperture. And with this example, that is easily possible. Well, on my notebook, the simulation takes about 17 minutes, but nevertheless, it's possible. I have the Gaussian input beam. Then here my diffuser element, my 4-level phase function. Then here my aperture, blocking stray light model with a 500 micron soft edge. Then I also simulate how does the field look like directly behind this aperture. You see it here, real with a speckled pattern, not just a convolution, here the real pattern. Here's the E field. And then in about 14 meters distance, in a tilted position, I get my nice pattern. And if I show it also in, again, the logarithmic reverse rainbow color scheme, you see with the indicated optimization region, which indicates also the projection area, that we have no light out, that everything is blocked. And inside we still have a certain security margin, and we have the pattern and also the cutout zeros order. So nicely done. So now every one of you have the options to project the Lighttrans logo on your building. So thank you very much that was it for my presentation of this today's webinar.